Hello, my name is Owen Haynes, and today I'll be presenting Physics 2212's Lab 3, Magnetic Field of a Bar Magnet. So the purpose of this lab was to measure how changing the orientation and distance of a magnet from an observation location affected the strength of the magnetic field it exerted. So the ultimate results of this lab are that we found the mu value was 5.853 amps times meters squared, and the N value is minus 2.3812. So the fundamental principle used in this lab is the Biot-Savart law, which is the formula that calculates the magnetic field. So we have a general formula for any location, and then we also have the formulas for the perpendicular and parallel axes to the dipole, and then the mu value is just the magnetic dipole moment. So first we had to set up the experiment. Our phones have a magnetometer in them, but we have to align them with Earth's magnetic field to make sure that the magnetic field that we're measuring is only coming from the magnet, not from Earth. So we first had to rotate the phone to align it with Earth's magnetic field, and then we had to locate the magnetometer within the phone by moving the magnet up and down and finding when the phone read out its maximum possible value, putting tapes on the x and y axis of the phone, and finding where they intersect is where the magnetometer is. So this is ultimately where we found the magnetometer to be. So after that, we could actually get to data collection. So the lab asked us to find the distance with which we would have to hold the magnet to read out certain Tesla values, so 20 microteslas, 70 microteslas, and so on, and then measure that distance. And the ultimate goal of this was to find this equation on the top right. The magnitude of the magnetic field is some constant k times the distance r to some value n. Plugging all that data that we collected into the left on this Excel spreadsheet here, we got this line graph on the right, where the slope of the line is the n value, and then the intercept of the line is the natural log of that constant. So ultimately we found the relationship that we observed between distance and the magnetic field to be minus 2.3812. So now knowing this, we can calculate the mu value of our magnet that we were using. So the field we were measuring was along the parallel axis of the dipole, so we can get the parallel axis dipole formula, extrapolate this k value, and then sub in our k value that we found in the last slide to actually solve for our mu value, which is 5.853 amps times meters squared. So the next part of this lab was to compute the off-axis magnetic field of the magnet. So our setup involved moving the magnetometer in the x and y direction by a value d, and then recording the readout of the magnetometer on this Excel sheet in the bottom here. Then we wanted to compare how our code model would compute the magnetic field with the Biot-Savart law compared to our observations in the real world. So on the left here, we are just setting up our physical constants. We're creating the objects to represent the magnet, and then we're also defining a function to output the magnetic field of the magnet, given a mu value and an r value. And then on the right here, we're just setting up our observation locations where we want to compute the magnetic field relative to the magnet. Next, this piece of code establishes the off-axis distance of the magnetometer, and then similarly plugs that into the magnetic field formula and outputs it to these results here. So this is what the results ultimately yielded. You can see our computed off-axis field as well as our observed off-axis field. And you can see that they're actually quite different. So some sources of error could be other magnets in the lab contributing to the net ambient magnetic field. There are lots of magnets in very close proximity to each other, so they could have had effects on our magnetometer specifically. And then the phone could have not been perfectly aligned with Earth's magnetic field. We had to touch it and move it around, so we could have rotated it slightly and gotten that off. So we found ultimately these are the observations that ring true. When the magnetometer is far away from the magnet, it measures a near zero magnetic field because the magnetic field decreases with distance, so that's a true statement. And then as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. We saw those to be true. Finally, what if you hadn't oriented your experiment to compensate for magnetic north and instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? How would your results have changed? If this was the case, Earth's magnetic field and the bar's magnetic field would both contribute to the net magnetic field the magnetometer was reading. However, there would be no way to tell how much came from each source, making the data collected useless. And then what if you were to stick two identical magnets together, enter in, and run the experiment again? How would you expect your measurements to differ? Because of the principle of superposition, this would double the magnitudes found by this lab because the magnetic fields created by the two magnets would add together. Thank you.